Hello guys, so I'm Abhimanyu Singh and I'm first year student at IIT and we are going towards the fifth lecture of the gravitation chapter. We will be covering problems in this lecture. So we will be doing the problems. This is the first problem. It is based on electric field. So we start the first part of it. What was the first part? The first part. Let me read out the problem for you first. A solid sphere of mass m and radius r is placed inside a hollow spherical mass of m n and radius r. So a particle of m dash is placed on the line joining the two center at a distance x from the point of contact of the sphere. Find the magnitude of the resultant gravitational force due to sphere and strength. And there are three different cases. So the problem is a simple problem. It's just applying the formulas correctly. So we will first calculate the field and then we will calculate the force. Okay, so what is the field? Field in the first question, the particle is lying somewhere here, some distance x from the bottom. So it is inside the sphere and inside the cell. And we know that the uh, E due to the total E is due to E of sphere plus E of shell, the vector term. And we know that E inside the shell is zero. So we will just put it zero. And what is this electric field inside the sphere? It is G m mass of the sphere into distance from the center divided by the radius of the sphere cube. So the radius of the G mass of the sphere, which is just like what is the mass of the sphere? Small m and distance from the center x minus small r and what's cube r cube. And what will be the direction? It will be pointing towards r vector. It will be attractive in nature, most probably. Opposite to r direct vector. So it is just a modulus. We are discussing only the modulus. So this is the field. Now the force. What is the force? Force is nothing, just m mod e. We are talking all in modulus, not in like g m m prime x minus r divided by r cube. This is the final field. I hope we all get the point. Now we will move to the second problem. So what is the second problem? What is the second part? The second part states that we need to find the force when the particle is like outside the sphere but inside the cell. And here it will be the same formula. And here also the electric field due to the shell will be zero. So what is like it will be like norm of E of sphere, norm of E of shell, ka modulus. So it will be shell due to field due to shell is zero. Now field due to there is only a field due to the sphere. So it will be just like Gm small m by distance from the center is x minus small r plus square. What will be the norm of this? It will be nothing m into norm of E. It will be G m prime by x minus r square. Will you getting my point? Now we will move towards the third part. What does the third part say? Third part is about the electric field. It will be it will be E sphere plus E shell. We know that the direction is same, so we just need to the simple sum. So the field due to the sphere is Gm x minus r square, Gm x minus r का square. So electric field due to the sphere plus shell. So now what is this? This is the electric field due to the sphere, and this is the electric field due to what is the mass of the sphere? The mass of the sphere is small m and capital M. So okay, now the mass force will be norm of m into norm of E. Sorry, no, there will be no norm. G m m prime x minus r square x minus r square plus g small m prime x minus small r square. So now I think this problem is done, but this is a very fundamental problem. This let me tell you what concept does this problem involves. Let me discuss about these things. So this problem involves multiple concepts. This involves first electric field due to the sphere. which is gmx by r cube inside and gm by r square outside for sphere SPH. And for shell, it is 0. And outside it is gm by r square. Okay. And also the principle of superposition. Principle of superposition. This question involves the following three concepts. Now, the second problem. I think this is very important to build your understanding. And there are three masses which are placed at this is the equilateral triangle A. Now we need to find the potential energy of this configuration. As they are talking about work, we need to compute the energy. So, firstly, when potential energy is just about moving the charge from infinity to that point. So, when we move the first charge, there will be no issue. It will be just zero because it is just lying in space. And when the another charge will come, sorry, another mass replace everything charged by mass. So when the other mass comes, it will experience a force, an attractive force by another mass. So it will be like there will be some attraction, and we know that the potential the interaction energy is like gm by gm square by a. So it will be nothing but with a minus sign as the force is attractive gm square by a. Similarly, when we brought the second mass, there will be two charges. So capital M into minus gm square by gm by a, gm by a. So now the total potential energy is nothing but gm square by a, 3 gm square by a. And when in the final situation, M, 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 this is the triangle, this is the triangle, this is 2a, this is 2a, this is 2a. So we need to find the final potential energy. So we will be just replacing a by 2a. It is simple because only the configuration remains the same. Only the size is double. So we will be replacing a by 2a. So it will be like minus 3 gm square by 2a. And we know that. And we know that work done is nothing. Work done on the system is nothing. U final minus U initial. So it will be given by 3 by 2 gm square by a. It will be the answer of this problem. Now the third problem is also involving on work energy. We are giving a vector. So how do you represent this vector? It is just like this. So 2. Okay, I'm drawing it wrong. Let me erase it. This will be the vector. Here 2, here 3. This is the electric field vector. All the vector parallel to this will represent the direction of electric field. Now, what is our line? What does our line we need to move look like? When y is 0, when x is 0, y is minus 5 by 3. And when x is 0, when y is 0, x look like minus plus, sorry, everything is plus. So our line looks like 5 by 3 somewhere here and most probably parallel to this. So now we have like equation of line as 3y plus 2x plus 5. What is the angle between them? It is 0. So 3 times dy plus 2 times dx is equal to 0. dy is nothing but minus 2 by 3 dx. Now, what will be the work done? Is nothing but change in potential. Change in potential, which is nothing minus E dot dl from initial to final position, where dl is nothing, dx I cap, dy j cap. So we will do the dot product now. E is 2i cap plus 3j cap dx x I cap dy j cap. Now we have 2 dx plus 3 dy. We do the dot product correspondingly. Now from this is equation 1. Let's say it. From 1, when we put the value, like we will be getting 2 dx minus 2 dy. You can see it. I hope you can see it. This is common arithmetic. So this is done. Now we will move towards the third problem. So this is a simple problem. We have discussed that the value of G is nothing but the value of electric field at, no, sorry, the field gravitational field at that point. G at R is equal to E at R. So now, at height above in the south pole, it is nothing but G minus 1 minus 2HR. Under the approximation, H is much less than capital R, which is the radius of. But let me do it capital R now. And when in the case of rotation, G is nothing but omega square R cos square theta. And here the cos theta is 0 as we are at equator. So we need to find Gs is equal to G theta for a H. Yeah, this should be valid for a H. So let us solve it. Let us take out G common. It will be easy for solve. So G with G will get cancelled. 1 will get cancelled. 2H by R is equal to omega square R by G. So H will be nothing but omega square R square by 2G. This is similar kind of problem we used to get in like expression when the fluid is like this and we are rotating it. This is a similar expression. You can refer to fluid mechanics there. This was a similar for height. Now this is very important problem. This is Earth. First, it is moving towards east to west, which is in direction of rotation of Earth. So as it is at rest, as there is no relative motion, V is equal to omega R, where omega is 2 pi by 24 hours, time period of rotation of Earth. In the second problem, the most important part is making a FBD. So it is moving like this with velocity V, and here is the tension, here is the mg, and here is like it is moving in a circular orbit. So we know that for circular orbit, sigma f external is equal to m a cm. So what is the external force? So assuming to be a positive direction, m v square by r, or we can write that also as m omega square r. Now for the third most part, it is very important. So as it is moving in opposite direction as it is moving at relative speed v, if speed is v, then v net is v plus omega r. You can just do it like a vector sum. It is simple one. So now sigma f is nothing but m plus v omega v mv square but a r. What is the force? Force is still same T minus mg. So m v square by r, m plus 2 m v omega. Now from the previous expression, we can substitute mg as T naught minus m omega square r. As v is very high, very low as compared to r, we are neglecting this term. Neglecting. So this expression comes out to be m omega square r plus 2m omega v. So t minus t naught is nothing, 2m v omega. You can find the expression of t. T is nothing, 2m v omega. This is somewhere similar to the Coriolis force. We, if you have solving like HCMY, you have seen something like Coriolis force. Coriolis force is just like pseudo force, works in rotating frame when relative velocity is there. Now this is a simple problem like t square, t square, 4 pi square, r2 square, r2 cube by 4 pi square, t square is equal to 4 pi square by gm. We know that we don't know about the value of gm. So we will be like finding gm from this equation. First equation. Now we need to find the value of g. G is nothing but gm by r1 square. So the substituting value of r1 from there, we get something like this. So the value of g is nothing 4 pi square r2 cube r1 square by t square. Now this is a data-based problem. I don't think like I remember the data. So I think we will do it in next class. So this is very important problem. This helps in building the fundamental concepts about how rockets work, everything, etc. etc. So now, let- as there is there is no friction, no loss of energy takes place. That implies E initial is equal to E final, where E is equal to KE plus PE. So we will be computing the initial kinetic and potential energy and final kinetic and potential energy. So initially, the particle when it is at surface of Earth, it is nothing. The potential energy is minus Gm by R plus half m V initial square. And when the particle reach at the highest most point, it just has the potential energy as its velocity becomes zero. And as h is equal to 6400 kilometers, it will be nothing but 2r. So half mvi squared is nothing but gm by 2r. Mass of, where m is mass of the Earth and m is small m is the mass of the particle or the satellite. We do the computation. Vi is nothing but gm by r. So I think we are it for today's problems. Now we will be studying something new. Actually, I would like to you give a brief idea about how in general central forces work. Like gravitation is a central forces. There are multiple central forces. Like electrostatics is the central forces, electrostatic forces. So there is a general theory of central forces which govern all the central forces. So I would like to give you a brief idea about central forces, which would further motivate you to dig deeper and develop more knowledge about it. So we will be doing central forces. Central forces. What does central forces mean? Forces which only depend not only inverse square law upon distance from a point from center. Okay, these are the central forces. And few of the fundamental idea is that in central forces, it is always a planar motion. Like there is always a plane in which the entire motion takes place. Due to this, we always get a angular momentum conservation. Why angular momentum conservation? I can explain you. We know that tau is nothing but dl by dt, nor and tau is also r cross f. What is it? Is the cross product. And what is the angle between r and f? It is 0 degree. So what has happened? R norm of f sine theta n cap. So what does sine theta brings it? Brings it to zero. So what does become zero? dl by dt is zero. So dl by dt is zero implies L is conserved. L is conserved. L is conserved. Energy also remains conserved. Unless and until there is mention of friction, air drag, etc. We assume energy to be conserved. So we have an idea of central forces, which is like a very nice idea. So I will be doing a simple derivation, which will involve some results. I will be not deriving them. I will be just writing them simply. R double dot in polar coordinates. We have the acceleration along the radial direction as R double dot minus R phi dot square. R cap. This is the acceleration in polar coordinates. Do you know what is polar, spherical, and cylindrical coordinates? So I will be doing just a brief introduction of this. We have polar coordinates. Then we have spherical. There are three types of common coordinate transformation we do. These are like coordinates in which the axis moves. For example, when you do ijk, the axes are static, but in these coordinates, like the axis moves. X is equal to r cos theta. I think you have know of this. If you have studied coordinate geometry, you must know of it. This is like y and x. This is r distance, and this angle is theta. It is nothing. It is just component r cos theta and r sin theta. And for spherical, we have x coordinate is equal to r sin theta sin phi, r cos theta sin phi. Z is r sin phi. So how do we derive in like spherical coordinate? This is like z, y, x. So this is the vector. The angle this is okay, this is phi. I'm wrong here. So this angle is phi. This is r. This is theta. This is theta. So how do we derive it? Like you can Google on like about spherical coordinate system to know more about it. I'm just doing a very short intro. I know you don't understand in this short intro, but it will be like when we talk about z component, it is nothing but r and cos phi. And when we do the sin phi, it is in the xy plane, and then we take a component along x-axis, and then we take a component along y-axis. Similarly, we have like a cylindrical coordinate in which we assume of a cylinder of height z. So the z component is nothing z, and the x component is s cos theta, and y component is s sin theta. These are the three common coordinates. In these coordinates, axes don't remain fixed. So we are writing acceleration in spherical coordinate. So now r double dot vector is nothing but r double dot r phi dot square theta cap. Now, sorry, r cap. Now we know that on multiplying both sides by m, we get m r double dot minus r phi dot square. Okay. Now we have now we are writing this. We can write it as grad of v. Okay. We know that f is equal to ma. Also, gradient is nothing, just I think it's tough for you. Del v by del x, I cap, del v by del y, j cap, del v by del z, k cap. It is the gradient of a function. So we just write it like this, and we do some differentiation, and we find out that v, which is the potential, has new form, which is v effective, which is comes out to be v naught plus x square by 2 mr square. Now we do the analysis, like the total energy, which is E naught, which remains the constant, is equal to half m r dot square plus V effective, not V naught. We have simplified it. So we do the analysis. So this is like this. So and when we do the further derivation and solve the differential equation for r, which you surely we won't be knowing, 1 by r comes out to be m alpha L square 1 plus epsilon cos phi. This is very tough, I know, where epsilon is 1 plus 2e L square m alpha square. Okay, I know this is like very shitty things, but I know these experience expressions might scare you, but I encourage you to look for them. Like it's physics is not limited to like what you are studying. You can explore more if you would like. Now I will be what I will be doing is I will be giving you a brief about what we have studied in this chapter till now. I think we have done like good number of problems. We will be discussing more of them. I will give you a brief what in the next lecture what kind of problems we will be discussing. But mostly I will be trying to review what is the stuff right now. What is the stuff we have covered till right now in a short and crisp manner. So let us go in a fast manner. First, we started with Kepler law, which has three laws. First is ellipse, that the particle that the sun revolves that the earth revolves around the sun in elliptical orbit with sun at one of its foci. Second was p square is equal to a cube. The third was like the uh, law of areas. dA by dt is equal to constant. That implies a planet sweeps equal area in equal interval of time. Area in equal interval of time. Now when then we move towards like Newton. What was Newton's law? Newton's law states that the force of attraction is product of the masses and inversely proportional to the radius distance of the square of the distance between them. From there, we find out force to be G m1 m2 by r square, where J is universal gravitation constant. Its value turned out to be 6.67 into 10 to the power minus 11, which is Newton meter square per kg square. The unit is. Then we defined like the quantities such as field, where field is nothing for finding. It is the force on unit mass. We define field, and then we find a field for common shapes. It involved ring whose potential are given as minus gm by z at distance z, distance s, distance r, distance z. It was gm by z. Then we find force, and due to this, I hope I am not wrong. Please, don't. I don't remember this. Don't look. I will tell you. Then we look for shell. Potential due to shell was constant inside gm by a, where a is radius of the shell, and it was nothing. It was like gm by r outside the shell. Right? For field, it was zero inside this, and outside it, it was like this gm by r square. For solid sphere, potential inside was quite interesting one, and outside one was nothing but gm by r square. And electric field terms are to be gm x, where x is distance from center and r is the radius of the sphere, and outside it just behaves as a point charge. These are the common fields, and then will study variation in value of g at height at height h above. The value of g becomes g prime, and g prime is given by gm by r plus h ka square. So we have the value of g prime on doing some simplification as 1 minus 2h by r. Under the approximation, h is much less than r. Now if we move h depth inside the earth, the expressions came out to be gm r minus h by r square, r cube, sorry. The expression is like this. And when we simplify it, it came out to be g into 1 minus h by r. It is visible and it is not approximated, it is exact. And when a particle is at latitude theta, then we have then we approximated the value of g prime as g minus omega square r cos square theta. How do we evaluate omega? Omega is 2 pi by 24 hours, which is 24 into 60 hours, 60 minutes. Okay. Now, then we studied about the relation between V and potential. This is the most important relation which you will come across in this chapter. Trust me, this is very important. Change in potential E dot dl, and E is equal to del v by del x I cap del v by del y cap del v by j cap del v by del z k cap. And then we did two standard problems. Now we studied about how to solve for orbits. Like we studied about circular orbits. Like the velocity is given as root gm by a, and the time period holds a relation like 4 pi r square a cube by gm. Now, and we also did that we can approximate ellipse as similar to a circle of major axis a. Okay, like there it is distance as a plus ae, there it is a minus ae, there it is 2. We can approximate as a circle of radius a. And then we talked about the energy, like energy E naught. So if a particle is thrown with a velocity, great. Then we discussed about escape velocity. The velocity needed to send outside the gravitation field of an object to the outside the gravitation field of Earth, which came out to be this. So this was this. And then we study how do we decide orbit. If this is like V naught, if V is equal to V naught, circle. If V is greater than V naught, but less than V, ellipse. If V is equal to V, parabola. If V is greater than V, uh, hyperbola. These were the three cases we discovered, and then we also did energy conservation. How do we calculated the escape velocity? It was like this. Suppose initially it have half mv square minus gm by a, and finally it has no velocity plus no potential energy as it is outside the electric field of Earth. So v comes out to be 2 gm by a. Then we did accurate analysis for elliptical orbit. Like this is R1, this is R2, this was V1, this is V2. So we did like R1 V1 is equal to R2 V2 from the virtue of angular momentum. Also, the another equation is like minus G M M by R1 plus half M V1 square as energy remains conserved minus G M M by R2 plus half M V2 square. So if there are four variables in which three will be given, we need to like two will be given. We need to figure out the remaining two using these two equations. We did it. We also studied about black holes. We also studied about the areal velocity, which came out to be dA by dt is equal to L by 2m. How did it? So also we did the derivation. I won't be doing the derivation. We studied about black holes. What does black holes have? Black holes have velocity greater than the escape velocity. It is like gm by a. Mass is very high, but we see where that is c is 3 into 10 to the power 8. Light can even escape. Is very high, it is very low. So this quantity very high. Okay, light can't escape. So like this is the crunch of the chapter. Uh, so today we did like basic problems. In the next class, we will be doing some good problems. So let me give you a brief outway of view. We will be discussing about what is the energy as the object, why the spherical objects are considered to be stable, why they have like energy stored in them. So we will be studying about self energy. These are advanced topics, and also about gravitational pressure. Suppose this is a sphere. It is just like made by the several disks of dr layers. A sphere is made of just by its several disks of different layers. So when assembling various layers, the previous layer must exert some force on the other layer. So there should be like some pressure. So we will be calculating that pressure. Also, we will be doing twin star systems, which are very important if you see JE is concerned. It was recently is asked in JE those 21. It was asked in like JE 15. Exact problem, direct problem. So these topics are asked, and I will be doing distance of closest approach as well. Many of you have encountered in like the chapter of atomic structure in chemistry, and you will be also encountering it in modern physics. These are commonly asked. So these are the four problems we will be doing in the next lecture, and I hope this concludes the chapter in gravitation. If you have any doubts, please free to ask. Is anyone there? So there is no one. So I hope I'm done for today.